u cosine v squared plus u sine v squared. And then we fill in the magnitude of its cross product, that's square root of 1 plus u squared. du, or dv rather, du. So now that's the integral written in terms of u and v, which is almost ready to evaluate. And well, what does this whole thing simplify to?
1 plus u squared?
Yeah, just 1 plus u squared, because here we have u squared cosine squared plus u squared sine squared. That just becomes u squared. So we have the square root of the same thing twice. Yes. All right. So now you can integrate that, which I won't bother doing. It's kind of plug and chug. More so than usual. No, because with every permutation you give, you got to compute this. You got to do all that every time for a problem like this. Plug and chug into your integrand. Now after that, once you get to this point, you know, this particular one's easy, but after that, yeah, that's where the plug and chug ends. Unless you're lucky enough to actually differentiate the thing, and then you can plug and chug with the limits. So there's that big gap of hell in between. All right. So that's the drill for integrating a scalar value function over a surface. Compute the magnitude of your normal vector, so that's just v steps, bing, 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 bing. Then take your integrand and write it in terms of your parameters, use a parameterization. The limits on u and v give you the limits for your double integral that you're now going to compute with respect to u and v, and then hope you can do the integral. Questions about that one?
Approach rocket.
Now that's how you handle a scalar value function. There's also a matter of how you integrate a vector field over a surface. Now, a while back we talked about how you integrate a vector field over a curve, so I'm going to refresh your memory on that. It's kind of similar in spirit. All right, so when we wanted to compute the work done by a force that was represented by a vector field as it moved the object along a curve, what we arrived at was the integral over a curve of a given vector field f turns out to be, we assume the same parameterization is used, t goes between a and b. So we're integrating from a to b. We have our vector field with parameterization plugged in, dot product with the tangent vector, not normalized. So that's what you do for integrating a vector field over a curve. Now for a surface, it's almost similar, but instead of dealing with a tangent vector, we're now dealing with the normal vector to the tangent space. Again, just like we were doing for scalar value functions. And so for surfaces, we have double integral over surface of vector field. So this is just how it's written. It's just notation here. It doesn't tell you how to evaluate it. But the integral of a vector field over a surface turns out to be double integral over the parameter space, so the domain that you have for u and v. And then you're going to have your vector field with your parameterization plugged in, R of u and v. Dot product with, so instead of dot product with a tangent vector like we had for curves, now it's the dot product with a cross product that you compute to get your normal vector. So in both cases, you're plugging into parameterization into your vector field. There's going to be a dot product involved, tangent vector in this case, be normal vector in this case. So the normal could be tangent plane. And then integrate with respect to your parameters, u and v. So, once again, plug and chug up to a point. You got to compute RU and RV from your parameterization. You got to compute your cross product, compute this dot product. For limits, that depends on where the parameters are defined, u and v. So setting up the integral, you can follow those same steps every time. Bless you, bless you. I guess that's bless you squared. And then whatever you get, that's what you got to integrate. Good luck. So now before I step through some examples of this, I want to mention a few applications or physical interpretations of this. So suppose that your vector field, rho v, where v is a velocity field of a fluid, and rho is the fluid density. Okay. Then, what that means is that rho v, this can be interpreted as the rate of change with respect to time of flow of mass per unit area. If you think of a fluid crossing an interface, like crossing a surface. Surface. All right. Okay.
So in your notes at the bottom of page 3,
Yep.
there's like the second to last step, an RU cross RV absolute value.
Yeah.
It cancels out with the other one, but where did the second one come from?
Oh, the second one comes from the fact that, this actually comes from how we define area of surfaces. Because if you have, so this is really from last time, if you have a rectangle parameter space that's mapped to a surface patch, so the area is ds. The area of this rectangle is dA. So ds, the area of the surface patch, is roughly RU cross RV times the area of a rectangle.
Alright.
Yeah. So this came from when we derived the area, the formula for the area of a surface last time. So this describes a rate of change of the amount of fluid that's crossing crossing a surface per unit area. Then suppose you have a surface patch S, and you have fluid going directly through the surface. So it's directed, like for instance, if you're pointing a hose right at it, then the amount of fluid passing through is the density times the velocity.